All right, let's go get started. Today we're going to go over priority queues, which is an abstract data type, not one of these concrete ones that we've been talking about. In other words, it's not an array, linked list, or a binary tree or whatnot, or all the other ones we've talked about, but it's an idea of how a data structure should behave. So, for example, our stacks and our queues were the idea of how a data structure would behave, but you could implement a stack and a queue with an array or a linked list. So this is a priority queue, which is just like a queue except for you add priority. Namely, when you insert something, it has a priority so it knows where it goes in the list. So if something is more important than something else, it'll be shifted to the front of the queue. And remember, queues were first in, first out, so a queue, and we call them lines here in America. But here it'll be priority. Where do y'all use priority queues?
I know they use them on the military base because whenever I have to get medicine, they'll put the active duty in front of everybody else, even if they show up an hour later.
That's right. Mm-hmm. Yep. Anyone else? Beal? No? All right. There are other places. You could, same thing with printing jobs. Similarly, if someone has a higher priority on printing jobs, they'll do that as well. There's a lot of places where these are used. Ooh, we get a little, wow, so I have to keep pressing the arrow. These were stolen from Java, so ignore that whole comparator or comparable because we don't care. But a queue, you remember, is first out, first in, first out. Whew. But a priority queue is least first out, so the smallest element is the first one removed. So this may seem inverted to you, but what that means is the element with the lowest number has the highest priority. So, yeah, you construct it, you can add something, you can remove the least, removes and returns the least element. You can get the least, return it, but don't remove it. You can ask if it's empty. You could ask for how many elements are in it. You can clear them. So Java actually has a priority queue. Huh. Does this look familiar yet to anyone? Nope? Okay, that's fine. So we're going to choose a data structure. It's good to look at patterns. So if we load an array once and do 1,000 searches on it, we'd want the search to be fast, so we'd probably sort the array. Let's see. If we load a huge array and don't only do a few searches, we probably don't want to spend time sorting it. For almost all uses of a queue, including priority queue, we eventually remove everything we add. All right. And hopefully this doesn't give it away.
Are you about to ask which one to use?
So, yeah, what do we use?
I personally think linked list would be better.
You think
can
list?
Sort as you're inserting it, and then it's already sorted.
Let's.
to insert.
All right. Let's. I like this. This is great. Let's do that. So. But the most important thing before we start doing the analysis is notice that we're not just doing add and remove, we're doing both adding plus removing, because with priority queue you're adding things, you're removing them, adding and removing, you're doing both at the same time. So it's actually very important that we do both. So let's go and write this big O up here. So it's add/insert is the most, we're adding to the priority queue. I'll call it priority queue. So it's PQ add/insert, so you know that you're adding with a certain priority. And then, of course, you're doing remove least.
Which will be the first one, right?
Depending on how you set up your data structure. All right. Okay, so you set a linked list. So linked list, what would adding be in this linked list?
1. Oh, 1.
Remember, we have to add with a certain priority, so we'd have to traverse down the linked list until we find the spot and put it in. Right?
Yeah. So worst case would be in, but I don't think in would be the average case.
It would be the average case because on average it was supposed to be halfway down. You go halfway down, n divided by 2 is still O of n. But as you're probably getting to, removing the least is pretty simple because you just remove the first element that's O of 1, right? Okay. Anyone else? Not necessarily the best. And here we like to avoid O of n if we can. Any other ideas? No other ideas? Let's do an array. Of course, this one has to be sorted. And technically, this one's sorted too. So if we want to add to the array, it's sorting. What can we use to find where it needs to go? If the array is sorted, because we're maintaining a sorted array, finding an element is an O of I know it's Monday. It's okay. We got this.
If it's sorted, I think we said it's O log n?
Correct, because which type of searching can we use?
Because we can use binary search
Right.
to start cutting in and out.
Right, so we can use a binary search to find where it needs to go, and then we have to insert it. How long does it take to insert into an array? In the middle?
Oh, then.
O of n.
Because
So-
we're shuffling
So
it.
Because
it's
we gotta,
still-
we gotta
But no,
shift.
shifting.
It's okay. I'll just keep telling you until you get it. Shift everything down. So even though finding it is log of n, shifting is O of n. So it ends up being O of n. How about removing the least? Now,
Oh, 1.
if you make it your array so that the least is always at the end, that way you can just decrement the size, then it would be O of 1. If you're terrible at coding this, you'll be O of n because then you have to shift everything down. But hopefully you choose the O of 1 solution in order to do this. All right, great. Well, what's another data structure we used?
Binary search tree.
Our binary search tree. Okay. What's the adding on a binary search tree? So you have to add it in order. So
O log n.
for average and best, worst it's O of n. Average and best is O of log n, right?
Right, assuming they haven't thrown everything on the one side.
Correct. Correct. And then for removing the least, you have to find it, don't you? Yeah. How long does it take to find it? You just keep going down the left side, right?
Yeah, I think it's.
Couldn't you set it up to where the least would be at the top instead?
In a binary search tree?
Yeah,
Not
I mean, it
in a
might be
binary
weird,
search
but-
tree. No, but you're on the right track.
Oh,
You're almost got it.
it's a heap. It's a reverse heap. There's something like that.
Well, hold on, we'll get to that in a moment. Let's finish the binary search tree.
It's O log.
Remember, you have a binary search tree.
Would it be O of n because even n divided by 2 is still n?
Well, you have to go all the way to the left, right? As long as this one has nothing on this side, then you know he's the least, right? And so you just remove it. So how long does it take to go from here to the least? Well, yeah, in the worst case, everything is a linked list going this way, which makes it O of n. Did y'all see that? And then the average in the best case, so that's the most interesting A I've ever written, is of course log of it. Okay. And what was the next data structure we were going to do? Heap. All right. So a heap, if you recall, you have to maintain the heap priority. So that the top element always maintains the heap priority, and in which case we'll make the heap priority the least, right? The lowest. So if you want to add something, you add it to the end of the array, and then you sift up. And what does that make it? I'm sorry, what does that make the big O complexity?
Worst case O of n.
For the heap, we use, well, why would it be O of it? How about?
Because if you insert it at the back and then it ends up being the least value, then you'd have to shift all the way up. into the
Right, but
top.
in a heap, how long does it take to sift
It's
up.
O login
It's,
because
you remember how you're
contains
sifting
balance.
up? Because a heap is really a binary tree. So when you sift up, you're dividing it in two or jumping up by two. So it is O of log of n. Huh, that's good. How about to remove? You swapped the first element, which is the least, with the one at the end, and then you sift down. So the swap is 1, and then how long does it take to sift down?
Log in.
Log n. Okay. So who's winning so far?
Heap.
The heap's winning. What's the other data structure we used?
Hash table.
Hash table. We need to add or insert it based on priority. Sure. Does that even make sense? No. How long would it take to remove the least? We'd have to scan the whole hash table, right? Right? I mean, is anyone not following me? We'd have to go, because the hash table, it has no ordering to the numbers.
It's
just
either we have lists for every spot, and we have to look through every list for the least, or
we have a giant
to-
array, and then we just keep looking until we find it, because there's no sorting to it. So you have to look through the whole thing.
And even then, what are we quite looking for?
Just one.
The one with the lowest value.
Mm. Yeah, I don't think that's what we
No, so a hash table is a terrible idea in this situation.
I want to see somebody try to implement that. That'd be fun.
I'm sure someone will online. Online guy, you got this.
Don't do it.
Don't do it. Don't do that yet. Okay. So, and have we done anything else? I think those are the 5 main ones, right?
Yeah.
Yeah. So who wins?
Heap.
The heap wins. How about that? All right. So array implementation, we could do unsorted. Adding an element would take O of 1, hooray. But removing would take O of n. This is an unsorted array. Hence removing and adding will take O of n, so this is not good. We could do sorting. Adding an element would take O of n. Why? Because as we pointed out up there, you do a binary search to where the element is located, and on average it's somewhere in the middle, and then you'd have to shift all the elements down, which is an O of n operation. But removing would be O of 1, because if you keep the least at the end, then you just remove the end. Takes O of n. All right, let's do linked list. Could be unsorted. Adding would be O of 1, because you just shove it to the beginning. But then removing is O of n, because you have to find it. And if it's an unsorted linked list, you just have to go through the entire linked list. Sadness. If it's sorted, adding takes O of n time, because you have to go through the whole list to find where it needs to go. And then removing an element would take O of 1, because hopefully you just keep the end or the tail to be the least. And then you can just remove it, because it's a linked list. And O of 1. All right, basically summarized what we just did on the board. Everyone good so far? Perfect. So, as with array, everything's O of n. They're inefficient. We could do a binary tree. Insertion is log of n to O of n. Why? Because a binary search tree, bless you, could worst case turn into a linked list. And so that's not desirable. We could do a balance one. And so how's everyone's balanced binary tree implementations coming along?
I'm done.
You're done? You did the project, or you're done with doing the project, or both?
I did the project.
Okay.
It was submitted. I have made my performance graphs.
Great. So how are those balanced binary trees?
They worked.
If you had to code them from scratch,
I think I would hate doing one of the ones that I did.
which two did you use, by the
I
way?
used Treat and Splay.
Oh, okay.
Splay is not something that I would want to code on my own. Treat, I think I would be fine with coding on my own.
Okay. Cool. We have to have an algorithm to rebalance it. Good rebalancing algorithms require only log of n, but are complicated. So we're kind of shying away from this, but maybe a binary tree or a binary search tree would work. But then the heap comes along. In order to do this, we define the heap property, just like the heap sort. Hey, look at that. So that we have the heap property being the lowest element. So it's just a binary tree. And you remember a heap was a binary tree that was it balanced and left justified where every node maintained the heap property. So in this case, the heap property is the parent is less than its children. Hey, look, we're going to go through the representation of a heap again. To add an element, we went through this last time. So I'm going to skip all this. Hey, and here's the nice thing. The STL has a heap, and since we've already done the heap before, you can use the STL heap moving forward, just not on the heap lab, of course. Right? Yes. A heap is a vector that has been heapified. Yes, I don't know why that's their term. That's what we get. What's nice is you use the make heap function to heapify a vector, and then further pushes and pops are done via heap function. So pushback is pushback plus push heap, and then pop is actually pop heap. So it's a little tricky because you have to keep in mind that pushing is really two function calls, not one. But besides that, it's pretty much the same. Good old example code. Hey, let's go do this. Let's do a class code. Let's do we have a template? Yeah. What day is this? Is this 19 or 20?
This is 20. 19's due Wednesday.
Okay. No, this is day 19. There we go.
Day 19.
Mm-hmm.
Why do we have more labs than days?
Because I've assigned 2 labs on one day.
Fair
When
enough.
did you do that?
At the beginning of the course, remember after the hurricane?
Yeah, but currently the days on the YouTube channel match up with what lab you were doing. On
Oh,
that
that's
day.
nice.
That's why I was thinking today was 20.
All right, we'll go to 20. Dot dot, there we go. 19 heap to 20 heap. All right, then we'll go into 20 heap. All right, so let's create a vector. Int nums. All right, let's have some numbers.
5.
All right, someone logged in already. Thank you. Comma. Sorry.
There's a 20.
How many numbers do you want?
Let's go with 10. So we have 1, 2, 3, 4, 5, 6, 7, 8. 2 more. All right. Okay, so now we need to create a vector. I forgot how this was done. I think something vector sub int. Oh, we gotta make it std, of course. Vec. Pass again nums, comma, nums plus 10. Sure, that's how it works. Let's see if that compiles. It compiled. All right. Let's go print it out. Oops. What am I doing? I'm doing, yeah, vec sub I. I'll do a little new line right there. Let's run, see if it prints it out. Warning, that's fine. That's okay. All right. So that's what it looks like. So then we can call, was it make heap? Make that heap. Make underscore heap vec.begin, because it has to have an iterator to the beginning of the heap and an iterator to the end of actually the vector. And then we'll just print it all out again. Alright, let's see if that worked. Nope. Make heap was not declared in the scope. So we need to include whatever file that's necessary, and I certainly don't remember what it is. It's probably like functional or something. Algorithm. Ooh, it looks like I've looked at this before. Algorithm. Alright, right up there. That's where it tells me. Let's run it. And accidentally press too many things, so hang on a second. Okay, so let's see, does this make sense? Is 104 bigger than 81 and 76? Yep. Is 81 bigger than 40 and 15? Yes. Is 76 bigger than 20 and 3? Yes. And then 40 needs to be bigger than 11 and negative 3, and then 15 needs to be bigger than 9. Yes, so that's a heap. Perfect.
But we need to reverse it, right?
Oh yeah, we have to reverse it. Maybe. That's a good question. What does my lab require? Let's find out. Let's see, pop. It doesn't say. Well, one moment. That is not what I want you to do.